In this video, I prove the following result. I prove that for all positive integers n, there are less than 2 log 2 n over log n primes between n+1 and 2n. So I start with a positive integer n, and I consider a prime between n+1 and 2n. So first, the prime is smaller than 2n, so it divides necessarily factorial of 2n. But factorial of 2n is also the square of n factorial times 2n choose n. So p divides n factorial square times 2n choose n. But p does not divide n factorial because n factorial is a product of numbers which are smaller than p. And p is prime, so p cannot divide this product. So p divides the other factor, 2n choose n. So p divides 2n choose n. So 2n choose n is divisible by all primes between n+1 and 2n. And then it's divisible by the product of these primes. So it's larger than or equal to the product. Okay, 2n choose n is larger than or equal to product of primes between n+1 and 2n. If I look at this product, so all factors of this product are larger than n. And the number of factors is the number of primes between n+1 and 2n. So I denote it by k of n. And then the product is at more than n to the k of n. So 2n choose n is strictly larger than n to the k of n. But on the other hand, if I expand 1 plus 1 to the 2n, by Newton's formula, I get that 2 to the 2n is the sum of 2n choose k for k between 0 and 2n. And then it's at least 2n choose n. So 2 to the 2n is at least 2n choose n. But 2n choose n is strictly larger than n to the k of n. So if we combine the two inequalities, we get n to the k of n strictly smaller than 2 to the 2n. Then I take the logarithm. So I get k of n log of n smaller than 2n log of 2. And then I divide by log of n. So I get k of n smaller than 2 log 2 n over log n. So it means that there are less than 2 log 2 n over log n primes p, such that n+1 smaller than or equal to p, smaller than or equal to 2n.